Hi dear students, welcome to today's online class. Today we begin a very interesting module in physical chemistry, that is module number 1, the solid state part 1. And in today's class we discuss some fundamental concepts related to solid state, the types of solids, and what is crystallography, and what are some important terms in connection with crystallography, and 3 laws of crystallography. Let us start with the classification of solids into 2 types, that is crystalline and amorphous. You know that solid and liquid states are condensed states where the constituent particles are held close. In solids, particles are closely packed, but based on the degree of randomness, we can classify solids into 2 types. One is crystalline solid, which is also called the true solids, and the other is amorphous solid, otherwise called pseudo solid. Pseudo means false. Amorphous solids are also called supercooled liquids because they are more like liquids in many properties. What are the differences between crystalline and amorphous solid? You know that. See, looking at this arrangement, you can see here there is a regular repeating pattern for the arrangement of particles. The constituent particle present in a solid, which we call in crystallographic term as motifs. Motifs are the structural units, which can be atoms, ions, molecules, etc. What are the differences? Number 1, there is a regular pattern. There is a perfect order of arrangement of particles in crystalline solids. Complete order is there, which repeat over the entire space. In amorphous solid, there is no regular repeating pattern. You can see that. It is something like, in a fruit shop you can see 2 types of arrangement of fruits. One is a heap of fruits which may be sold out for a low price. Another a more costly fruits which are kept in a perfect order. Like that. In crystalline solids, particles are regularly arranged. You can see that order everywhere. But here they are close but not in a perfect order. This is shown for simplicity. Actually, particles are more close. Second point is the order of arrangement. The order is long range order. In crystalline solid, you can see this repeating pattern, order of arrangement throughout the crystal, throughout the solids. So it is said to be long range order. Whereas in amorphous solid, you may find some order somewhere, but it is not repeated. So it's called short range order. If at all there is some order in amorphous solid, it is not repeated all over. So it's called short range order. Third point is very important. Crystalline solids have got sharp melting point. Whereas in amorphous, there is no sharp melting point. Rather, amorphous solids on heating, it will melt over a range of temperature. First they soften and then melts over a range of temperature. A good example is you can see plastic. When you heat plastic, it slowly softens and melts over a little wide range of temperature. And another important difference is that crystalline solids are anisotropic. What is meant by anisotropy? Physical properties like electrical, thermal conductivity, refractive index, etc., which are different in different direction. That is called anisotropy. If these properties are same in all directions, means independent of direction, it is called isotropic. Amorphous solids are isotropic, whereas crystalline solids are anisotropic. It is obvious from the arrangement. See, if you check a particular property like refractive index along this direction, it will be different in this direction. Why? Because the particles which we encounter along this direction is different from this direction. Here, since there is no perfect order, on an average, it will be same in all directions. It averages out. That is why melting point also like that. Here there is a sharp melting point because the kind of binding force is uniform all around, but here it's different because of the difference in the order. And in addition to these differences, there are more differences like crystalline solids give clear cut. If you cut with a sharp knife, you can cut in a regular fashion. But amorphous solid gives an irregular cut or cleavage, or what is called conchoidal cut. Crystalline solids can withstand compressing forces to a large extent, but amorphous solids cannot withstand compressing forces. They may even flow under gravity. You can see in the case of glass, in long run, glasses which come under amorphous solid become thickened at the bottom and thinner at the top. In the case of window panes. Okay, so these are the differences between crystalline and amorphous solid. Most of the solids belong to this category, and you can see the examples: diamond, sodium chloride, copper, metal, sugar, etc. I have put here 4 different types of crystalline solids. So you have a question. You have a question to do. That is, you have to differentiate 4 different types of crystalline solid, which is based on the type of constituent particles or motifs and the binding force present. That is, diamond belong to which category? It's covalent crystals because it contains carbon atoms. Sodium chloride belong to ionic crystal which contain positive and negative ions as the constituent particles. Copper belong to metallic crystal, that's a special type. Sugar belong to molecular solids, and most of the solids belong to these molecular solids. All the organic compounds come under this molecular solids, or all the covalent molecules are able to form molecular solids like sugar. So you may differentiate these 4 types of solids. The question is, what are the 4 different types of crystalline solid and what are the differences between them? Okay, they differ in the constituent particles and also differ in the type of binding force. Due to that, there is a lot of difference in their properties, various properties. So you do that as a homework. Example for amorphous, you can see plastic, glass, rubber, resins, many polymers all come under this. Okay. Now, next we go on to the technical terms. Actually, this module involved discussion of crystalline solids or 2 solids. So we have the term crystallography. It is the branch of physical chemistry dealing with structure and properties of crystals. In crystallography, we come across some terms like crystal habit, crystal phase, crystal plane, interfacial angle, then space lattice, unit cell, and many more terms. We will come across more terms later. Okay, look at this model. You can see this is a cubic shape. Suppose this is a cubic crystal. Okay. Crystal habit means the shape, the geometrical shape of a crystal. So this is cubic. There are different crystal habits like tetragonal, orthorhombic, monoclinic, etc. That we will discuss later. Crystal phase is the bounding phase of crystal. The bounding phase. Interfacial angle is the angle between adjacent phases. Suppose you take this phase and this phase. What's the angle? It's 90 degree here. It may be different in different crystal habits. Crystal plane is the planes passing to the motifs, passing through the structural units in a crystal. So this is a plane passing through these four particles. This is another plane. It can continue in a big crystal. This is another plane. You can imagine a plane like this, a dihedral plane like this. So these are crystal planes. We have a lot about crystal planes later. Then space lattice. These two terms are very important, which you are familiar with even in your plus 2 courses. What is space lattice? It is the regular arrangement of points which shows how the particles are arranged in a crystal. See, for example, in this cubic crystal, we can show 8 points. 1, 2, 3, 4, 5, 6, 7, 8. What is the importance of these points? These points are regularly repeating. See, if this distance is A, actually in a crystal it is repeating. So there will be another point here and it repeats. So repeating points. And you can see this point is repeated along x-axis, along y-axis, along z-axis. So three-dimensionally. That is why space lattice. So space lattice is, what is space lattice? It is the regular arrangement of points. Regular arrangement of points. Regular arrangement of points, okay, three-dimensionally or in space. What is the significance of these points? Which shows how the particles are arranged. Like there are particles at the 8 corners if we have points here. Sometimes there can be point inside here. We call it body-centered. There is another lattice point. So lattice points are the regularly repeating points in space which shows how the particles are arranged in a crystal. Then the next term is unit cell. What is unit cell? See, in a crystal we can see a basic repeating unit that is called unit cell. Like for example, in our daily life, if you make a wall using a brick, using bricks. Okay, using bricks you are making a wall. One brick is a unit cell because that brick is repeated along the 3 axes. One brick is the smallest building unit of that wall. Like that, in a crystal, the smallest repeating unit of a crystal, which when repeated over the entire space, means along the 3 axes, build up the crystal. Right? Suppose this is a unit cell. It is repeating like this, repeating like this, repeating like this also. You get a big crystal. That is unit cell. So unit cell is the smallest repeating unit of a crystal which when repeated over the entire space build up a crystal. Now we have to discuss 3 important laws of crystallography. There are 3 important laws of crystallography, and these laws are related to the geometry of crystals. The first one is law of constant interfacial angle. Law of constant interfacial angle. This was put forward by Steno, so it's also called Steno's law. Okay. This is is talking about interfacial angle. What is interfacial angle? Angle between adjacent faces of a crystal. The law says that interfacial angle of any crystals of the same substance will be a constant. That means the same substance you can grow as crystals in different size and shape. For example, look at this. A very simple representation, a 2D representation only. Suppose this is a crystal, a hexagonal crystal of a substance, and I am growing another crystal of the same substance. How can you grow crystals? How can you grow crystals in different shapes? By changing temperature, solvent, various conditions. So these are two different shapes. The law says that the corresponding interfacial angle, that's very important. Corresponding interfacial angle will be the same. Suppose you are taking this angle, this interfacial angle, you have to take the corresponding angle, this one will be same. So I repeat, Steno's law says that the corresponding interfacial angle of different crystals of the same substance will be a constant. So that is telling you that a substance will maintain its crystalline properties even in different conditions. See, we discussed previously about crystalline and amorphous solid. Actually, the same substance can be made to exist as crystalline or amorphous by changing conditions. For example, silica. If silica is melted and then it is slowly cooled, it will form its crystalline form, that is quartz. Quartz is one of the crystalline form of silica, you know that? It's crystalline. But if you take silica, it is sand contains silica. It is melted and the molten silica is immediately cooled without giving sufficient time for crystallization. What will happen? That will become amorphous. It will form the amorphous state, and that is what we call as glass. So glass is the amorphous form of silica, whereas quartz is the crystalline form of silica. So the same substance can be made to exist either in crystalline or amorphous form by changing temperature and other conditions. Now coming to another law, the second law, that's again regarding the geometry of crystalline solids. The law is law of symmetry. See, you have learned about symmetry, that is molecular symmetry. Symmetry is also applicable to crystals. Crystal symmetry is also important. Each crystalline shape is characterized by certain symmetry elements. The law says that the elements of symmetry of different crystals of the same substance will remain constant. Again, similar to the first law. It's talking about the constancy of the geometry of geometrical pattern of crystalline solids. So, law of symmetry says that the elements of symmetry of various crystals of the same substance remain the same. We can take example as cubic crystal. See, this is how we draw a cube in a flash, drawing two squares displaced and joining the corners, you know that. And this is a model. Most of the crystals are cubic, or we are more concerned with cubic crystals in our discussion in the syllabus. Now what are the various symmetry elements for this cubic crystal? For a cube, we can consider various symmetry elements. First of all, let us consider the axis of symmetry. See, if you take an axis passing through the center of opposing phases, right, like this, and you rotate, what is this proper axis? I mean, what is the order? It is C4, right? So, there is C4 axis. How many are there? Since we are connecting opposite phases, a cube has 6 phases, right? 2 phases make up one axis, so there will be 3 C4 axes, right? See, to have a mental picture, you consider the room you are sitting, okay? So it is like you are inside a cube. You can see the 6 phases, 1 up, down, 2, 3, 4, 5 and 6 phases. Then coming to the next symmetry element, I mean proper axis is, see, consider an axis passing through opposite corners, okay? Consider this axis. And now look here, you look from here, see how many times the same appearance is coming. You can say what is this order? This is what? C3. So one C3 is obtained by joining opposite corners. How many corners for a cube? There are 8 corners, right? You can count in your room all the corners. 1, 2, 3, 4, 5, 6, 7, 8. Joining opposite corners give one C3 axis. So how many total? There are 8 corners. So there are 4 C3 axes. Then what is the next symmetry element? Now you consider an axis passing through opposite edges, okay? This is one edge, this is an opposite edge, right? This edge. And now you look from here, see the appearance. Suppose I am holding like this, see the appearance. See how many times it is repeating and rotating. How many times? It is C2 axis. One C2 obtained by joining opposite edges. How many edges for a cube? How many total number of such axes? There are 12 edges for a cube. You can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You count in your room the edges. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So you need imaginations in discussing crystals, of course. So there are 12 edges, so there will be 6 C2 axes. So there are how many? 13 proper axes. Now coming to the planes. See, here we have some different terms we use. Vertical plane sometimes, here it is called a rectangular plane. There are, this is one rectangular plane bisecting this cube. So passing through 2 opposite phases. So there will be 3 such rectangular planes. So 3 rectangular planes. Okay. Then in addition there is another kind of plane that is passing through opposite edges, bisecting the cube like this. This is called dihedral plane or diagonal plane, like that. How many opposite edges give one dihedral plane? So there will be 4 such, because there are 8 edges. So 4 dihedral plane. Okay, dihedral planes. So there are 7 such planes. Finally, a cubic crystal has a center of symmetry, of course, isn't it? Because you know, this point is the center of the cube. You can do the inversion operation. So there is one center of symmetry. So total you have 21 symmetry elements. Sorry, this dihedral plane is not 4. Since we are connecting opposite edges, edges are not 8 but 12, so there will be 6. So this is 9. So it comes to 23 elements. So a cubic crystal is characterized by 23 symmetry elements that remain constant if you check any crystals of, for example, sodium chloride. Sodium chloride is cubic in shape, and if you check any crystals of sodium chloride, you can see that it contains 23 symmetry elements. Okay, so these are the two laws. Now the third law is about the crystal planes, which is to be discussed in little detail in the coming class. Thank you.